and welcome to Beyond the Gates. I'm Annette Kirkland, and this season we're going to be featuring Today, Tomorrow, Always. We will highlight how ERDC is delivering impactful solutions today, driving innovation for tomorrow, and prioritizing people always. From groundbreaking research to enduring partnerships, we explore the power of progress rooted in purpose. Today, I'm going to be speaking with Brent Towne. He's a research civil engineer with the ERDC Geotechnical and Structures Laboratory, otherwise known as GSL. And we're going to be talking about On the Move, how ERDC powers the future of military mobility. Good morning, Brent.
Good morning, Annette.
How are you?
I'm doing good.
I am so happy to have you on the show this morning.
Thank you. I'm glad to be here.
And so, we get into like this serious subject, but not so serious. We're going to talk about you.
Okay.
So I want you to dive into telling me about yourself, your background, and your role at ERDC.
Okay. Yeah, so I started working at ERDC in 2005 as a summer intern under the Cooperative Education Program. That's what it was called back then.
You're not going to count the years, right?
That's right. So started working as a student in the Geotechnical and Structures Laboratory, Mobility Systems branch. While I was going to school, I finished up at Mississippi State with civil engineering and started working full-time with ERDC, same Geotechnical and Structures Lab with mobility in 2007. So my whole career has been with the Mobility Systems branch, and my primary role there in mobility has been performance testing with military vehicles, so taking these vehicles out and seeing how they perform in different conditions and making sure those vehicles are tested to the requirements that they were designed to.
This might sound lame and everything, but I think that sounds like a fun job.
It is pretty fun. Yeah, I never thought.
And interesting and fun.
That's right.
You're in you probably test so many different types of these military vehicles.
We do. Yes, we've tested vehicles from very small, lightweight, 4-wheeled vehicles, up to your 100,000-pound combat, tracked vehicle systems. So it's a wide variety of vehicles that we've tested and modeled. So it's been very interesting and fun a lot of times to be able to take these new technologies and see how they perform.
Okay. All right, so here we go. ERDC has conducted mobility research for decades. Can you start by explaining what advancing military mobility really means for today's Army?
Yeah, so ERDC first started in mobility many decades ago, back in the 1940s actually, around the World War II time frame. So our role at that time was to try to develop the methods and the tools to be able to assess vehicle trafficability. So we had to understand how soils affected vehicle performance, both on-road and off-road. So ERDC, we were WES at the time, Waterways Experiment Station, had a 2 decades long of research to be able to develop those methods, to develop those tools. And those tools and methods were standardized, and that's some of the same methods that are being used today. A lot of those methods that we developed back then were transitioned over to the Army test centers, so the proving grounds. We help develop those methods, and the test centers do a vast majority of testing from slope climbing to ride quality, soft soil performance. So there's a vast array of tests that they have to go through at these proving grounds before the Army will acquire these types of systems. And we help test those vehicles. We do a lot of the soft soil performance testing today and work with the test centers to make sure that these vehicles can perform before they go into the soldiers' hands.
A lot of prep work. Lots of prep work.
Yes.
So how does ERDC help the Army make sure vehicles can go anywhere they're needed, whether it's across mud, sand, snow, or even flooded terrain?
Yeah, so that gets back to that, the standard test that we have to perform to be able to do this. So like I mentioned before, ERDC does the soft soil performance testing for most all vehicles that are being acquired for the Army. whether it's prototype vehicles that the Army is looking at to replace older and legacy systems, or existing systems that just need upgrades. So we take those systems and do vehicle cone index testing, which is it's a performance metric that these vehicles have that they must meet to be able to go off-road and say like swampy, marshy environments. So that test we do right here at ERDC.
Okay.
We have a test site over north of Vicksburg. It's right on the Mississippi River. This site floods every year, so it provides ideal conditions that are needed to be able to test in these types of conditions. So we take the vehicles over to this site. We prep the lanes, and we have equipment to be able to support this type of testing. And then take the vehicles out and run the test. We have the tools and equipment needed to characterize the soils. So we're looking at how the soils affect the vehicle's performance. And in this particular case, the requirement for these vehicles is that they must meet a particular soil strength. They must be able to make a certain number of passes on this soil strength before the Army will say it passes or fails.
Okay.
And we do that test to make sure it meets those requirements.
Data-driven, too.
It is, yeah. And that data also feeds a lot of our models that we have developed to be able to predict these performances for the vehicles. So not only are we testing them, we have tools that have been developed to be able to predict where they can and can't go off-road.
Wow. So mobility is more than just the vehicles. It's also about the ground, the weather, the infrastructure. How do you bring all those pieces together to support Army missions? You notice these questions are just loaded, right?
Yeah.
I had fun trying to get these.
Yeah, so absolutely. The ground plays a big part in how the vehicles are going to perform. Our soldiers don't have the luxury of being able to operate these vehicles on road networks and infrastructure designed to support these military vehicles. So we have to be able to understand the conditions that the vehicles are going to maneuver in so that we can make sure they can get from point A to point B, because that's critical for the Army, all the military services. They have to move troops from point A to point B. They have to move equipment, supplies. So our job is to develop the models to be able to predict for these specific areas, mission related. These models have to account for the soil types, the various soil types, the various soil conditions, the environmental conditions. We have to factor all that in because soldiers are going to use these vehicles in some of the harshest environments. So we have to make sure that our models that are predicting how these vehicles are going to perform account for that and are realistic. And this just ensures that the vehicles, when they're finally fielded to the soldiers, are going to be able to operate in those environments. And so the infrastructure is the same way. Road infrastructure, we have to account for different types of road profiles. Road profiles play a big part in how the vehicle rides, so we have to account for that, because if the vehicle rides too rough, it's not going to be able to keep up with the pace that's needed during military type operations.
If it needs to go fast.
It needs to go fast.
Right. Okay.
Yep.
But, ERDC uses virtual test environments to evaluate these vehicles. So how do these simulations save time and resources compared to traditional field testing?
Yeah, so like we were talking earlier about all the different conditions, when you're talking about different soil types, different soil conditions, different types of terrain, that plays a big part in the vehicle's performance. And if you're trying to design tests and control these tests, all those different variables are hard to control in field experiments. Typically in the field experiments, we like to test the boundary conditions, but we can't account for all the different variables during a field experiment. It would just cost way too much to be able to do that. So we rely on our modeling and simulation tools to help supplement the physical testing and that reduces the amount of cost needed. You still have to have the physical testing.
Right. But I'm sure it reduces it dramatically.
It does, yeah. Physical testing for one platform can take a couple of years.
Really?
And just for the standard types of tests that they have to do going through, like the vehicle acquisition programs. So that's tests that are required. So there's all these other conditions too that you're kind of uncertain how vehicles are going to perform in those areas, and that's where we rely on modeling and simulation to fill those voids.
Okay. So can you tell us about the NATO reference mobility model, otherwise known as NRMM, and why it's, we're all about acronyms with the government, and why it's still such an important tool after all these years?
Yeah, so the NATO reference mobility model is the standard modeling and simulation tools used by the military. It was developed back in the 1970s and has been improved and upgraded over time, and still enhancements are being made to it to this day because it is still the standard M&S tool that's used for vehicle mobility within the Army. That tool was developed, like I talked about earlier, all the different research that was done, testing done over 20, 30 years back in the 1940s. All that data was used to develop the NATO reference mobility model. So that tool also accounts for different types of vehicles. So you have to have a tool to be able to build tracked vehicle models, wheeled vehicle models, and anywhere from, like I talked about earlier, the light vehicles up to your heavy, 160,000 pound tracked vehicles. So there's a vast array of vehicle systems. So that model can account for those different types of vehicles. Then the terrain is another piece of it. You have to be able to model the terrain. Like I said, you're not going to be running these vehicles most of the time on nice developed road systems. So the model, the NRMM model, you can build large terrain data sets and pull those into the model. And then environmental conditions you also have to account for. So like different seasonal conditions throughout the year for specific areas, because the drier the season, typically the better the conditions are going to be on some types of soils. If you're in a sand and a dry, that's bad. If you're in a clay during dry conditions, that's good. But vice versa, if you get wet conditions on a sand, that can be a good condition. Whereas if you get wet conditions on a clay, those can be very bad.
Is it because the sand goes like in stuff too? I mean, like in the vehicle and all that, or is
it's just that the mechanical properties of the soil fail when it's in a dry condition, a dry sandy condition, and it's the same with wet clays. It's all it all comes back to the soil strength condition, and moisture plays a role in how the soil behaves, and soil behaves different under different moisture conditions. A sand behaves differently than a clay behaves. So we have to be able to characterize that and make sure our models can predict for that, and the NRMM does. So all of those different variables have to be accounted for, and NRMM can do that, and it's being used to predict go and no-go performance anywhere in the world. As long as we can get the data that's needed for those specific areas, the tool can be used to predict performance.
And that's great that you can still use a tool that was used many, many, many years ago. So.
Yes. The only thing is we have to continually update that model, because new technology brings in advancements in different types of vehicle systems. So we have to sometimes make sure the model can ingest these new types of vehicle systems. Updated terrain data, we have to be able to ingest that. So there's continual enhancements to
sort of like an app. You got to update an app, right?
That's correct.
It's just the same thing with technology like that. ERDC is home to some incredible high-performance computing capabilities. How do we use that technology to to with, with vehicle modeling, to with. Misprint on my part.
Yeah, so when we're trying to simulate in these complex environments with the different vehicle types, or even one vehicle can have several different configurations. That vehicle can be used as a utility vehicle, or it can be used as a combat vehicle. So there's different variants. And all of these different variants perform differently in different conditions. So you have to simulate for those different types of vehicles. And then there's just the terrain data that you have to pull in. So when you're talking about doing simulations for really large areas, like several kilometers, sometimes hundreds of kilometers wide, those are very large data sets.
I'm sure.
And then now you factor in environmental conditions, like different seasons of the year. Your simulation just grows exponentially to a point where your standard computers cannot run those simulations. So the HPC allows most of the time for those simulations and those different variables to be run. But a lot of times it's just speeding up that process too, versus running these simulations on a standalone type computer.
That doesn't even work.
No, like I said, most of the time you wouldn't even be able to run the simulation.
Right.
The data is just too large.
Right. So ERDC also studies autonomous systems and robotics. And how do your simulation tools help make unmanned vehicles more reliable on the battlefield?
Yeah, so we have a tool that we developed called the Virtual Autonomous Navigation Environment. With that tool, what we do is model the sensors that these autonomous vehicles have on them. We model the vehicles, we model the environmental conditions, and pull all that together in this virtual world. We at ERDC, we don't develop the autonomy itself, but we work very closely with autonomy developers. And that's what this tool was developed for, was autonomy developers, so that we can integrate their autonomy software with our sensor models, with our vehicle models, with our terrain models, into this virtual world where they can bring it in and see how the autonomy is going to behave in these extreme environments. So in these virtual worlds, we can bring in rain, dust, snow, fog, all of these different environmental conditions that are going to affect the sensor performance on these autonomous vehicles. So it just provides a tool so that our autonomy developers can assess those vehicles in a virtual world, which it again goes back to the time and the cost to test these vehicle systems. It's hard to go out and test all these conditions. So this virtual world provides direct feedback to the autonomy developers to see how their algorithms on these autonomous vehicles are going to decide to maneuver through these complex environments.
And just like you brought up, so you have partners that work together on these projects to get this research done.
Yes. Yeah, we work very closely with the Ground Vehicle System Center. They do a lot of the autonomy development for the Army. They do a lot of physical testing with those platforms. So we utilize the data that they're collecting on those platforms to make sure our models are predicting accurately. And then also transitioning our tools over to them so that they can help speed up the process of developing these autonomy vehicles.
Wow. So ERDC has tested everything from joint light tactical vehicles to mine-resistant ambush-protected vehicles. What have we learned from those studies, and how does that knowledge directly impact soldiers in the field? So
those are two examples of kind of two different acquisition programs that we were supporting at that time. The JLTV program, that was a new prototype vehicle that the Army was looking at, high mobility multi-purpose wheeled vehicles. So that vehicle had to go through several testing phases through the acquisition process. And we were there to do the soft soil performance testing to make sure it met those requirements for that particular vehicle. So there are many phases it had to go through, and we were just there to support, and provide support through testing, modeling and simulation also. So if I back up a little bit, during the early stages of that acquisition process, they have to set the requirements for that vehicle. Our modeling and simulation tools are what are used to kind of assess the performance of those vehicles and set those requirements. And then we go into testing them once they start building the prototypes. So that was a new vehicle system that went from concept design all the way up to production level. That we supported. The MRAP program was an example of a vehicle that was already fielded, started to experience some issues with mobility in Afghanistan and Iraq. It was a very heavy vehicle. It was up armored, so it had trouble maneuvering off-road. So we worked with the programs office for MRAP. They came to ERDC and was like, what can we do to help improve the performance of these vehicles? So we looked at different running gear, which is just the tires on the vehicle, and made suggestions on the path forward to be able to improve the mobility. And then they came to us to test those systems with those improved tires and different components on the vehicle. And through our soft soil testing, we showed that there was a significant improvement in the vehicle's performance off-road. And then those vehicles were ultimately fielded with those new technologies and improved the mobility of those systems.
It's a lot of testing.
Yes, we do a lot of field testing.
And do you ever just sit back and go, okay, 10 years from now, what will technology be like?
Yeah, it's kind of scary how fast.
Even almost 2 years from now, really.
Yeah, how fast technology is advancing. A lot of these newer systems or newer vehicle systems have some pretty advanced suspension systems, and just all the technology is pretty interesting.
Right. So understand there is a backpack-sized tool to help troops make faster go, no-go decisions on the ground. Can you talk about this special kit?
Yes. So when I was talking earlier about the different soil conditions that affect your mobility, we have to be able to measure those soils and or measure the properties of those soils. So this tool was developed to do that. And
developed at ERDC?
It was developed by ERDC, and it's basically a cone penetrometer. So cone penetrometers are not anything new. It's used a lot in geotechnical engineering to determine soil strengths for like foundation design and things. But the military needed a penetrometer that you could go out and quickly or rapidly collect data over large terrain areas to be able to assess if the vehicle's going to be able to go there or not. So this tool was designed to meet those requirements. It's basically a shaft 18 inches long with a cone tip on the bottom that a soldier can press into the ground to get a soil strength profile with depth. Because that's another critical piece of this. We can't just try to figure out what the soil properties are on top of the ground, because the thing that drives vehicle performance is depth. So we have to understand what's under the ground surface. And this tool, they can punch it in the ground and get different soil strength with depth. But also another thing that this tool does is it measures soil strength losses that you would encounter like in a very clayey soil. So when you drive a vehicle over a clay soil, it's actually decreasing the soil strength under the wheel loads. It's not compacting the soil and making it stronger, it's making the soil weaker. So the tool, this kit includes a tool that measures that as well. So with those two instruments, we can fully characterize the soil properties that are going to affect the vehicle's mobility.
Wow. We got a couple more questions and we'll be wrapping up. So We talked earlier about seasonal conditions like rain, freeze, thaw, cycles, or flooding can make or break a mission. How does ERDC help plan for those unpredictable challenges?
Absolutely, yeah. So our soldiers, they can't stop a mission just because it starts raining or it starts snowing or there's a river that they have to cross. They have to be able to maneuver. They can't stop. They can't become immobilized. So for these different types of conditions, we make sure that we've collected the right data to be able to understand how these conditions affect the vehicle's mobility. And for snow, for instance, we work very closely with our Cold Regions Research Laboratory here at ERDC. They developed all of the models for snow and ice. So the NATO reference mobility model that we talked about earlier, it accounts for those conditions as well. That's just another environmental condition that we have to make sure we're predicting for, in these models. And then, like you mentioned with the flooding, if our soldiers are trying to get across a gap and it's a river or a stream or whatever, and there's strong current in it, we have to make sure that those vehicles can ford that and cross it. If they can't ford it, then they have to go through other means to be able to try to cross those types of conditions. But we work very closely with our Coastal and Hydraulics Laboratory because they can predict for like stream flows and things like that. So we ingest that data into the model, and then we can use the vehicle's performance capability to predict whether it can cross in those types of currents.
And I'm sure people at ERDC and myself included love to hear how you guys work closely with other labs. So that's always so good to know that you guys work together to make these things happen. Yeah,
there's such a broad range of knowledge, within ERDC that we have to rely on the different expertise within the different laboratories to make sure that our models that we're developing are accurate. So, we bring all that knowledge together, and it makes a very robust and very accurate prediction tool.
Absolutely. Well, before I ask the last question, I do want to thank you for what you do for the military, for the nation. So it's very important, your work that you do, and so I just want to say thank you.
Yeah, thank you. Yeah, it's very rewarding to be able to work in this space and know that, the work that you're doing ultimately matters and is going to soldiers to be able to use. And so it's a very rewarding job to me.
I'm sure you go home, with pride, and that's such a cool thing. So in closing, are there any key takeaways you'd like our listeners to understand about this research?
Yeah, so with mobility, mobility is constantly changing. Like I mentioned early on, vehicle systems are changing. We've gone from very lightweight vehicles all the way now to autonomous vehicles and robotic vehicles. So things are constantly changing, and the terrains that we're encountering are constantly changing, whether it's the type of terrain we're in due to soil conditions or whether it's environmental conditions. Things are just vastly changing. So we have to stay ahead of the area of this research to make sure that all of the different variables that are going to be encountered with vehicle systems, that we understand it and that we can predict for it, because we can't send these vehicles out not knowing that they're going to be able to withhold, what they were intended to be used for.
Right. Well, thank you again, Brent, for being on this show.
Thank you.
And this has been very, very educational. Thank you for listening, and we'll come back at you next time with Beyond the Gates.